Hey, Wheaton North, Mr. Yergler here. We're going to talk about waters of hydration in this video. They're often referred to as hydrates, and these are salts that tend to absorb water into their crystalline structure. All right, we're going to actually do a lab regarding this as well. So we'll look at hydrate formulas. We will calculate the molar mass of a hydrate. Both of those things are pretty straightforward. Calculate the percent by mass of a sample, and then talk about the lab setup with a hydrate lab, and then be able to calculate the moles of water in a hydrated sample, especially in a lab setting. All right, so let's talk about these hydrates and what they are. Hydrates contain a specific number of moles in their crystalline structure. So you have copper sulfate, for example, and in copper sulfate you'd have copper ions, cations, and sulfate ions, anions, polyatomic ions, in this like crystalline structure where there's one of these and then one of those and then another copper and another sulfate, right? Kind of overlapping in this like lattice structure. Well, and this would be a salt, right? Any ionic compound can be referred to as a salt. Many salts are hygroscopic. They absorb water. They absorb moisture from the air. And copper sulfate absorbs 5 moles of water, 5 molecules of water for every 1 molecule of salt, copper sulfate. Okay, so here's a couple pictures to kind of show this, different ways of representing it. So this one is kind of showing, here's your copper atom, or it's really an ion, and a sulfate, and there's kind of water molecules that are kind of bound inside that structure. You have all these different ions kind of overlapping, right? Positive, negative, positive, negative, positive, negative. And those water molecules have positive and negative ends because it's a polar molecule. And so they kind of get locked into that structure with the ions. Here's another way of representing it. I think in this one, I think they're showing waters. The hydrogens are like the light pink color. And so this is like a water right here, or like this is a water kind of trapped in that crystalline structure. Okay, we can actually heat those water molecules out. Okay, and that's what we're going to do in the lab. And this is what copper sulfate pentahydrate looks like. When it has the water molecules, it takes on a different color because the water molecules kind of change the refraction of light, or the absorption of light, I should say, and then that changes the color, right? So copper sulfate it has this very characteristic kind of deep blue color, but when you heat it, when you drive that water off, it becomes very light colored because those water molecules are leaving. Now, how we do this is kind of the setup that we're going to be using. We're going to have a crucible on a ring stand over a flame, and we can use Bunsen burners or Meeker burners. This is showing a Meeker burner, which kind of provides the heat over a broader area. And we want to make sure we clean and heat the crucibles beforehand. If there's any moisture in there, that's going to add mass. So we want our crucibles we want to know that our crucibles are completely dry and clean before we start. Everything is obviously going to get very hot, so we need to be careful not to burn ourselves. The crucibles obviously retain a lot of heat after you turn off the fire. And then you want to make sure you reheat your sample to what we call constant weight. Okay, in order to be sure that we're driving off all the water, what we do is we heat it once until we're pretty sure we've gotten it all out, and we mass it, and then we just go ahead and heat it again. And if we mass it again and find that the mass has changed significantly, then that indicates that there was still more water that needed to be driven off. Right, so we're gonna heat it to constant weight. So that we know if the weight is constant, if the weight's not changing, then we know that there's water not leaving because it's already all gone. Okay, obviously you're going to record all your measurements. Now, once the hydrate is heated, you can calculate the moles of water that evaporated. Let's go back a slide. Think of it this way. This sample has the water molecules trapped inside. This one doesn't, right? We heated it to produce this. So if we know the mass when it has the water, and then we drive off all that water, and now we can find the mass after it doesn't have the water, we can obviously figure out how much water left, right? Now you have the mass of just the salt by itself, no water, and so you can kind of calculate kind of backwards, so to speak, figuring out how much water left, and then what was the mole ratio of the water to the salt. That's basically what I'm describing here. Calculate the mass of the hydrate, that's before you heat it. The anhydrate, that's after you heat it, and then you can figure out the water by subtraction. Then, of course, once you have those masses, we can figure out the moles of anhydrate and water separately, and then figure out the ratio of how much salt do you have in moles versus how much water did you have. It's always going to be 1. The salt is always 1, and so it's 1 salt for however many waters, right? Sometimes it's 5, sometimes it's 7 water molecules, sometimes it's 3. It could be a variety of numbers. Here's sample data. This is what the data would look like. You'd have the mass of your crucible, and then obviously when you add your hydrate, it gets a little heavier. And then your mass of crucible and hydrate, that would be after you heat it, after you drive off the water. From there, you can calculate the hydrate formula and the percent water if you know that the anhydrate, the salt that you're talking about, is copper sulfate. All right, these numbers your eyes kind of glaze over these numbers. Let me kind of talk you through this. So this is the mass of, the 28 is the mass of the empty crucible, right? So this is the mass with the hydrate in it. So just the mass of the crucible and the salt hydrate together minus the empty crucible. It's obviously going to give you the amount of hydrate you have. This is after it's heated. So after it's heated, minus the empty container would be the mass of the anhydrate. And then our difference in water, how many grams of water left. From there, we can calculate a percent mass of water, and we can also figure out the mole ratio of water, which is actually the more important thing because we want to know what the formula is for the hydrate. So convert your grams to moles. So now, just like an empirical formula type calculation, you would divide your smaller number by your bigger number. So in this case, we figure out that there's 3 moles of water. There's 3 times more water than salt, anhydrate salt. And so the formula is CuSO4, and then we use a little dot to indicate there's 3 waters of hydration attached to those molecules. So now we have the hydrate formula, and we can figure out the molar mass of it as well. The molar mass of the hydrate formula would be the molar mass of the salt, and then adding in those 3 waters. So the molar mass of water is 18, so 3 times 18. Add that to your molar mass. So hydrates, the presence of that water adds to the molar mass of the hydrate. So it matters how many waters of hydration you have in there. All right, this is Mr. Yerler signing out.